By now, I'm sure it seems like you've seen every type of approach possible. But wait, there's more. With the advent of GPS and the flight management systems on corporate jets and the Big Iron, we have a lot more navigational flexibility. The good news is that the FAA has created RNAV approaches to make sure we get full benefit from that flexibility. Now, RNAV stands for Area Navigation, and these approaches are designed to take advantage of the ability of GPS to take you directly to any point on Earth. For example, let's take a look at the plan view of a sample RNAV chart found in the AIM. Now, this is the RNAV Runway 17 approach to Norman, Oklahoma. Notice it uses the classic T shape that you've already seen on a GPS approach. By the way, the FAA will eventually convert GPS approaches to this same RNAV format. RNAV, as we've said, stands for Area Navigation, and of course, GPS fits that category to a T. The key to this approach is that it utilizes a concept the FAA calls Terminal Arrival Areas, or TAAs. When you have the capability of going directly to any point on the globe while you're IFR in the clouds, you need something to tell you how high to be so that you don't hit anything that's attached to the Earth. And that's where the TAA comes in. A TAA divides up the world in the vicinity of an RNAV approach into 3 areas and gives you a minimum altitude to use while going through each area. It's so simple that even I can understand it. Let's take a look at the TAA basic design. Surrounding the approach T, you see a semicircle coming off the T crossbar on the side opposite the long leg. It's called the straight-in area. Then, on either side of the T long leg, you see 2 quarter circles. The one to the left, labeled right base area, and the one to the right, labeled left base area. They correspond to base legs in a landing pattern. Each of these areas shows a minimum altitude. As always, you will find variations to this basic setup. Some TAAs may be missing one of the base areas, or even both, leaving only the straight-in area. And the straight-in area might be opened up to cover all but a maximum of 120 degrees around the final approach course. If you come in from a direction not covered by a TAA area, such as down here, you'll have to fly the published course reversal unless you get radar vectors. You may also see sectors within a TAA showing different minimum altitudes than the area as a whole. In this case, if you arrive from the northwest, your minimum altitude drops from 6,000 feet to 2,000 feet at 22 nautical miles from the initial approach fix. You'll find TAAs tailored as necessary for local terrain and obstructions. Most in Kansas will be pretty standard. On the other hand, those at the foothills of the Rockies may not be. Notice how on this approach chart they show the TAAs as a semicircle and quarter circles out away from the clutter. And each shows the initial approach fix waypoint name you'll use when you're arriving in that area. And your altitude? Well, look, it's printed right here on your chart, 4,000 feet for this TAA. When your approach includes TAAs, you're expected to go to the initial approach fix and fly the altitudes for the TAA appropriate for where you're coming from. If you're coming in from the north, anywhere from a bearing of 083 to 263 to first, you'd fly directly to first and then to later. If you're approaching from the southeast on a bearing of 353, around to a bearing of 263 to first, you'd fly directly to T-turn, then to first, and then to later. On the other hand, you could be arriving from the southwest on a bearing of 353, around to a bearing of 083 to first. In that case, as soon as you cross the right base area boundary, which in this case is the 30 nautical mile arc from Turtle, or when ATC releases you within the area, you'll use the right base no procedure turn setup for the approach by flying to Turtle, first, and later. Is that simple or what? Notice you never have to fly a turnaround procedure such as a procedure turn. You always just go to turtle or T-turn when arriving from the base areas. But what if you really want to fly the holding pattern for practice or to lose altitude? Then tell ATC, since they're expecting you to fly the approach without the course reversal. In that case, you'll go to first and fly the pattern as published. Generally, the area covered by the TAAs for an approach includes one or more airways, so you don't need feeder routes. But if all the airways lie outside the TAAs, the chart will include feeders aligned with the appropriate IAFs of the T. Now that we understand how to get started on this approach, let's drop down to the minimum section to see how low we can go. Well, the answer to how low you can go depends on how your aircraft is equipped. Notice that the minimums for Category A aircraft range from 1,760 feet down to 1,382 feet. Let's start at the bottom of the minimum section and work our way up. Using plain old GPS to shoot the approach and circling at the end lets you get down to that 1,760 feet. But if you go up to the next level, labeled LNAV, you can go down to 1,700 feet. LNAV stands for lateral navigation. This is the minimums level you'd use if you were equipped with a plain vanilla GPS like the L18 and making a straight-in approach. To move up to the next level and get minimums of 1,500 feet, you have to have LNAV VNAV. Now, VNAV stands for vertical navigation. What that means is you have to have a navigation system that internally computes a glide path for you based on how far you are from the runway. Some fancy navigation systems you see in jets have this capability. It won't be long until we see this capability in piston airplanes. Now, how do we move up to the next level, labeled GLSPA, with even lower minimums? Well, to do that, we'll need VNAV capability with even more accurate GPS than we have now. Remember earlier I called the magnificent KLN-89B a plain vanilla GPS? Well, that's because we will soon have equipment that will let us do much better. As you probably have noticed, all of the GPS approaches we have talked about so far have been non-precision approaches. Right now, GPS isn't accurate enough for precision approaches. It only gives accuracy to within 50 to 100 feet, while an ILS has accuracy to within 15 to 30 feet. But there is a way to improve the accuracy of GPS, and that is by having a transmitter that knows where it is located send out correction signals to the GPS units in aircraft. One system to do just this is the Wide Area Augmentation System, or WAAS. WAAS is a network of over 20 ground stations around the U.S. which will receive GPS satellite transmissions. Since each ground station is in a known location, the locations derived from the satellite transmissions can be compared to this known location, and any errors can be identified. This error information will be processed and sent to satellites in stationary Earth orbits. These satellites will then broadcast error-correcting information to the GPS receivers in aircraft. Now, that all sounds pretty complicated, but it should be unnoticeable to the users of GPS. What will be noticeable, however, is that this system will be accurate to nearly ILS tolerances on approaches. For even greater precision, LOS, or local area augmentation systems, will be used. These are very similar to a WAAS. But with a LOS, the error correction transmitters are ground-based instead of space-based, and they send the correction signals directly to the aircraft rather than relaying them through a satellite. Since loss correction signals will be limited to line of sight from the ground transmitter to the airplane, they will typically only cover an area within a 25-mile radius. So with that kind of capability, we will be able to step right up to the GLSPA level. GLS stands for, are you ready for this? This is complicated. Global Navigation Satellite System Landing System. The PA stands for Precision Approach. With that, we get the lowest minimums of all. In this case, 1,382 feet. Notice that the GLS-PA and LNAV-VNAV are labeled DA for Decision Altitude rather than MDA. That's because with the GLS-PA and LNAV-VNAV, you are following a glide path, whereas with the LNAV, you are making your descent on your own. Now let's go to the top of the chart and take a look at some of the notes. The first note says, circling not authorized southeast of runway 321. The next note reads, DME, RNP 0.3 NA. NA, as you know, means not authorized. DME refers to a navigation system that determines its location by tuning in more than one VORTAC or VOR DME and figuring its position based on how far it is from each. The problem is when you get lower, the system might not be able to receive information from enough DMEs to get an accurate position. That's probably why that system is not authorized in this case. The RNP 0.3 refers to the accuracy level of the system. RNP stands for Required Navigation Performance, and the 0.3 tells you that the system would be within 0.3 of a mile of where it says it is 95% of the time. That's the accuracy level you need for approaches. The next note says Baro VNAV not authorized below -20 degrees Celsius, which is -4 degrees Fahrenheit. Baro VNAV stands for Barometric VNAV. VNAV uses the barometric altimeter to know how high the airplane is in relation to the computed glide path. As you know, the altimeter does not give you the proper terrain clearance in extremely cold weather. So this system is not authorized in extremely cold weather. So there you have it, the RNAV approach. One more handy way into the airport of your choice with a lot of promise for the future.